Okay, so we're back working on our next lesson. You have your guided notes ready. And as I promised you last time, we're going to work now on some geometric formulas with fractions. The formula for the area of a triangle involves fractions naturally. Other formulas involve fractions because the measurements involve fractions. And of course, you've got all sorts of things that are fractional in the field of heating and air conditioning. We end up with ratios, which we'll talk about in a little while. Temperature conversions involve fractions. Fractions are all over the place. Okay, but today we're going to deal with the geometric formulas. So get your pencil and your guided notes and let's get ready to go. The first thing that happens with a triangle is that we need to talk about this idea of the word base. And base does not mean the bottom of a triangle. The triangle doesn't have to have a horizontal side. The horizontal side doesn't have to be on the bottom. We see it like that a lot because people are drawing on paper and it's just a natural human thing to do. So where's the base? Technically speaking, any side of the triangle can be designated as the base. Just imagine that you've taken a picture and you rotate it around. Whatever was on the bottom before has shifted, but you can still call it the base. So let's look at this triangle here on the left and imagine that we want to have this side as the base. So I'm going to highlight it in red. Maybe you make yours a little bit darker, but there's the base. The thing about a base is that the base is supposed to be perpendicular to the height. And sometimes it helps if we have an imaginary parallel line through that third vertex. So the height, as if this is a mountain. I wish I could rotate this for you, but I can't. So you just want to imagine this kind of rotating down so this base is horizontal. And think of this as a mountain. And we say, how tall is this mountain? And we would drop a perpendicular from the top of the mountain, that corner, all the way down to the base. And so we'd have a nice right angle there. And that would be the height of the mountain. So what we really have are two parallel lines here. And the height is that perpendicular distance between them. All right, so we should probably fill in some blanks up here. We're going to imagine a line through that third vertex. This is this corner here that's not touching the base. That is parallel to the side that we've decided to call the base. And the height then is the perpendicular distance between them. Oops, that's not a very good R, is it? Perpendicular distance between them. Okay, so what if this side here were the base? Can you find the height? Take a second, try to draw it in. So the first thing we've hopefully did was identified this as being that third corner. We've got that parallel line here. Some people like this parallel line, some people don't. If it doesn't help you, don't draw it in. It's not a big deal. But then from there, we want to go in a perpendicular way to the base. So the base is here, and the height is there. So if you rotated this triangle around so that the bottom was here, then the mountain would be this h distance tall. Try again. We haven't used this side for the base. See if you can draw in the height. Again, if this perpendicular line, if this parallel line through the third vertex doesn't help you, then, don't use it. But the idea is to go in a perpendicular way. It just helps me start off at what looks like a right angle, all the way over to the base. So there's our height right there. What's the lesson we want to take away from this before we flip the page? One big deal is that the height is always perpendicular to the base. Now I'm not going to write base here. I'm going to say the height is always perpendicular to the line containing the base. And the reason why I wanted to change it is on the next page. So let's flip over and see what could possibly happen here. If you have an obtuse triangle, it's possible that the height could fall outside the triangle. So let's look at an example. I'll put the base on the bottom just so it's easy for us to see. So this is sort of a leaning triangle, but the base is right here. How tall is this triangle? Well, we'd come up here and say, how tall is it? And of course we'd drop a little string or something straight down and say, well, it's this tall. And well, where is that? So we have this line that contains the base. In other words, we're going to extend this side so that it intersects with this perpendicular. The height is right here. Now the base doesn't come all the way out. It doesn't count this dashed stuff. It's still a side of the triangle, but the height is way over here on the outside. It really says how tall is it? How far is it from the top of this triangle down to the ground? Let's get that same triangle again. Or roughly speaking, that same triangle again. My drawing's not really great on this. What if I wanted the base to be here? Can you put in the height? Well, we'd find the third corner. Maybe you like this parallel line right there to help you get a sense of where that height should go. But it would be this one right in there. So depending on which side is the base of your triangle, the height can land inside the triangle or the height can land outside the triangle. As a matter of fact, sometimes your height can be on the triangle itself, meaning it can be a side. But that only happens with a right triangle, because you know that a right triangle has a lovely right angle built in. So if you call that side the base, perpendicular to that is the other side, which will be the height. In a right triangle, the height is not always a side. Just like before, it depends on where you put the base. Let's take that same triangle-ish and say, what if I decide to call the base over here the hypotenuse? Well, then we would have the height here. Right? We just want the bases and the heights to be perpendicular. All right, so why do we care about identifying the base and the height? All right, you're going to be outside. You have a triangular, I don't know, patch of ground. Maybe we have a triangular window. Maybe we have a triangular opening, right? Nothing's always vertical and horizontal. You have triangles in all sorts of orientations, and the side that you're looking at it from is just the side you're looking at it from, and that usually becomes the base. The reason why we care is because the area of a triangle is given by a formula that says 1/2 of the base times the height. A lot of people think about triangles as being half of a rectangle, but that's not exactly true. If you had a slanted sort of triangle and you put two of them together, you wouldn't get a rectangle, but you would get a parallelogram. And of course, the formula for the area of a parallelogram is just base times height because it's two triangles put together. Well, let's try this here. We had one like this and like that. If we take this triangle and flip it over so that this bottom side comes up here to the top, this left side comes over here to the right, and you see the lovely parallelogram. So it's not really half of a rectangle, but we get the same basic idea. Okay, time to get down to work with the formulas. In our first example here, we would like to find the area and the perimeter of this triangle. Oops, that was a little far. Sorry about that. Hang on. There, that's better. Okay, so we've had a lot of formulas before. You still need to know those. When you go back and you look at the reading for this particular section, you'll see a big list of geometric formulas that I'm going to assume that you know. When you memorize a formula, though, memorize it so that it feels like an equation. Say the area of a triangle is, and the perimeter of a triangle is, so that we don't get the wrong numbers in the wrong places. So here we go. The area of a triangle is 1/2 the base times the height. All right, we need the base. Where's the base? I'm looking for this there. Here's the height. That's the 41. And the base is the side the 41 touches. So the area is equal to 1/2. The base is 81. The height is 41. And we're just multiplying and calculating from here. Let's see. 1/2 times 81 times 41 is 1,660.5. $1,660.5 what? All right, so this is area. This was 81 centimeters multiplied by 41 centimeters, and centimeters times centimeters are square centimeters. Perimeter. Well, perimeter is what it's always been. It's just the sum of the side lengths. The thing that happens with perimeter is people look at this picture here and think they have to use every number in sight, which isn't true at all. We want the sides. So we would like 81 and 79 and 43. The 41 is the height, and that's on the inside, which is not part of the perimeter. So 81 plus 79 plus 43, and what are we looking at? 203. 203, well, this is 81 centimeters plus 79 centimeters plus 43 centimeters, and centimeters plus more centimeters gives us a whole bunch of centimeters. And there we go. We have an area and we have a perimeter. So you have a new formula then to add to your list of geometric formulas that you should know. Let's flip over to the next page. There, that should look a little better. We're still dealing with a triangle, but we don't have a picture this time. The area of a triangle whose base measures 7 1/5 inches, whose height measures 3 1/3. Whoops, that should say inches in there. We'll just fill that in. And we'd like to find its area. We don't need a picture. Many triangles fulfill these requirements. Many triangles have these specifications, and every single one of them will have exactly the same area. It doesn't matter if the triangle is obtuse or acute or right. Every triangle with a base of 7 1/5 inches and a height of 3 1/3 inches will have the same area. Okay, so here we go. The area is equal to 1/2 of the base times the height. So we have 1/2 of 7 1/5 for the base and a height of 3 1/3. And I know you have a fraction key on your calculator and it could do this really nicely, but we are still dealing with some fractions, and they're so much fun and exciting that we could probably just check and see if we can do this by hand. Yeah, it's good stuff. We have 1/2. We would need to take the 7 1/5 and write it as an improper fraction. 5 times 7 is 35, plus 1 is 36, so that's multiplying by 36/5. 3 1/3, 3 times 3 is 9, plus 1 is 10, multiplying by 10/3. Looking around for common factors. 2 times 5 is 10, so 10 is a common factor for the numerator and denominator. 3 goes into 36 12 times. I can do this faster by hand than you could typing it into all that fraction template stuff on your calculator. This is just 12. 12 what? These were inches times more inches give us square inches. There's the area of the triangle. All right, I know you want to do this on your calculator, so let's give it a try and make sure we can all type it in properly. Let's see, we have 1/2. That part's not so hard. If you like to multiply with the parentheses, that's fine. If you want to multiply with the multiplication key, that's okay too. But your mixed number is here on the calculator. Remember to use the second key in order to access it. All right, 7 1/5. Uh-oh, what did I do? I don't know what I did. Somehow I got out of this. Just get back in. There we go. 7 1/5. Hopefully that didn't happen to you. Close those parentheses. The calculator knows that parentheses next to parentheses mean multiplication, so don't worry about that. But we'll still get our mixed number template. 3 1/3. Come out of the fraction, close the parentheses, and there we are, 12. But I'm telling you, I did it faster by hand. You could too. All right, enough of that. Let's move on to the next one. The area of a triangle is 2 square feet. The base of the triangle is 5/6 of a foot, and we need to find the height. All right, so let's see. Start with the formula. Area is 1/2 of the base times the height. Fill in everything where it belongs. This 2 square feet, that's the area, and 2 belongs over here. Of course, 1/2 is just part of the equation, but the base here, we have 5/6, and the height is the unknown. All right, so we're looking at this, huh? Has that little feel of algebra to it, doesn't it? But we know what to do here. The first thing we're going to do is clean up the right-hand side. What is 1/2 times 5/6? Well, that's pretty fast and easy. That's 5/12. How do I get the 5/12 and peel it away from the h? How do I undo that multiplication by the coefficient when the coefficient's a fraction? Absolutely. We'll multiply both sides by the reciprocal of the coefficient. So I have 12 over 5 multiplied by 2. If you want to think of it as 2 over 1, that's fine. And on the right-hand side, we have 12 over 5 multiplied by 5 over 12. And of course, the h is still there. Right, 5 over 5 is 1, 12 over 12 is 1. That leaves us with 1h on the right-hand side. And on the left-hand side, I don't have any common factors, so we're just looking at 24/5. Well, of course, we wouldn't leave it that way. 5 goes into 24 times, or sorry, into 24 4 times with 4 left over, and there we are. 4 4/5. 4 4/5. Don't forget those units. Those are feet. And that's the height of our triangle. There, see, that algebra stuff comes in really handy, huh? All right. Yeah. Let's try. Well, I guess we have 2 more, don't we? Let's flip over to the next page. This is a really interesting example. We're in a position where we have some crazy house We need to do something about the ductwork, but everything is old and just strange sizes everywhere. In order to fit this duct inside the gap where it belongs, it can only be 5 1/3 inches wide. I mean, we could make it smaller if we wanted to, but this is as big as it can get. We'd like to fit in there nice and snugly, and we know for the airflow to be proper in the house, the area of the duct has to be 72 square inches. So what we need to do is take a piece of metal and actually fold this to create the duct. And in order to keep the two edges together, we're going to use a lap seam of 3/8 of an inch. And the question is, how long should the piece of sheet metal be before it gets folded? You could just try this a bunch of times, but that takes a lot of time and it costs money because you have to cut all this metal and then it's not the right size. Then we have to go get some more. Lots of trips to Home Depot happen in here. It's a whole lot better to draw some pictures and do some calculations. Saves us time, saves us money. All right, so let's get started. The very first thing I'm going to do is to make a picture of this rectangular duct. There. Gorgeous, isn't it? All right, so this is going to be 5 1/3 inches wide. And I don't know that side, which I'll call H because it's going up and down, its height. All right, what do we know? We know that the area is the base times the height because it's a rectangle. If you like length times width, that's fine too. It doesn't really matter. So we have 5 1/3 multiplied by H. And you see if I did this like this, I've got a little bit of a problem because now I'm stuck and I think I've done everything I need to do, when really what I should have done was look at my formula and fill in everything that I know. The area is supposed to be 72 square inches. All right, so 72 is equal to 5 1/3 multiplied by H. We want to undo this multiplication. All right, so just for the sake of time and to show you what you could do on your calculator, because you've got this great calculator that can handle fractions, let's see what it looks like if you actually divide both sides by 5 1/3. I'm almost afraid to do this because it looks really weird and it's counter to what I told you to do before. But you should learn how to use your calculator, so we'll do it this once so you can see. The most important thing is to make sure that you're holding that value in parentheses, that you're going to divide both sides by 5 1/3 as a single unit. So 5 1/3 over 5 1/3 is equal to 1. And here on the left-hand side, we have 72 divided by, and then grab that mixed number template, 5 1/3. If you were on any other calculator, you'd have to put parentheses around this 5 1/3, and you'd have to put a little plus sign in between the 5 and the 1/3, and it'd be a little more awkward. But this calculator is kind of nice. So there we go. We have 27 halves. If you want to see that as a mixed number, you know the converter is right here, and that would be 13 1/2. So we have now just found out that H is equal to 13 1/2, and of course those are inches. Okay, so this is 13 1/2 here, 5 1/3 here, and another 13 1/2 over here. Remember, we need to fold and create this duct out of a nice rectangular piece of metal. And this is what's called a stretch out. So I need a portion here that will become the bottom of the duct. That's 5 1/3. I need a portion here That will become the right-hand side of the duct. That's 13.5. I need a portion here that's going to become the top. Clearly this is not drawn to scale, but hopefully you're getting the right idea. 5 1/3. I need another portion here that's going to become the left-hand side of the duct. So there's 13.5. And then I need this last little portion for the lap seam, and that's 3/8 of an inch. That's how long this has to be. Okay, well, let's figure this out. And these are all 1/8 and 1/3. It's not that hard. We can do this one probably by hand pretty easily. Let's just do it because we can. You remember that in order to add fractions, we need to have common denominators. So I have denominators of 2 and 8 and 3. How about we use 24? The whole number doesn't change. 3 times 8 is 24, 1 times 8 is 8. That first fraction turns into 5 and 8/24. Why don't you pause for a second, fill in the rest of the fractions, add them together, see what you get, and then come on back. Here's what mine looks like. How's that look to you? All right, so now we're adding the fractions. 8 plus 12 is 20. 8 plus another 12 gives us another 20, so that's 40. We have 49/24. 5 plus 5 is 10. Plus 26 gives us 36. So we have 36 and 49/24, which we know becomes what? 36 plus 24 times 2 is 48, so that would be 2 and 1/24. And in the end, need a little more space down here. That will give us 38 and 1/24 of an inch. That's how long that piece of metal needs to be. We might buy it a smidge longer just to make sure we have enough to bend and, cut in any waste that might occur, but that's definitely our minimum length. All right, yeah, kind of cool, isn't it? Okay, last one before we go. We have a square window. The perimeter is 11 feet. The first question is, what is the area of the window? Well, I don't know. But we do know how to calculate the perimeter of a square. And even if we don't remember the formula, we can always draw a square and label everything and see that the perimeter is equal to 4 times the length of a side. And this perimeter is 11. And it's not hard to divide both sides by 4 so that the length of a side is equal to 11/4 of a foot. If you want to convert the 11/4 into 2 3/4, that's fine, but really I don't need to because this isn't the question. The question isn't what is the side length. We want to know what is the area. To calculate area, we need to take the length times the width. For a square, these are exactly the same. X times x will give us x squared. So the area is 11/4, right, for the length, multiplied by 11/4 for the width. That's not so bad. 11 times 11 is 121. 4 times 4 is 16. And then we have to do a little bit of division. 16 goes into 121 7 times with 9 left over. And those, of course, are square feet. One because it's area, and all units for area are squared. And the other one is because this is 11/4 feet times 11/4 feet, and feet times feet give us square feet. And there we go. But we're not done yet because there's a part B. We want to put trim around the window, and the trim is 2 inches wide, otherwise known as 1/6 of a foot. And we'd like to know how much trim is needed. And you might think that the answer is 11 feet because that's the perimeter of the window, but that's not really true. And we'll see this as soon as we draw a picture. So let's get our window back here. There's our square window. If you put trim around the window that was 2 inches wide, it would look like this. If all you had was enough to match the perimeter. And nobody wants their window to look like that. We need to have this in here as well. Now, I'm not suggesting that you have little tiny square pieces off the end, but this is what we need to draw in order to calculate the actual length of trim that we need. Because here, this distance is the side of the window. That's 11/4. Or if you want to say 2 3/4, doesn't matter. But over here, this is the width of the trim. That's a 1/6. And this over here is a 1/6. So the total length of a side looks like that. If you want to turn these 11/4 into 2 3/4, that's fine. It doesn't matter. It's all the same. If we have 2 3/4 plus 1/6 plus 1/6, that would give us 2/6. Then here we are in this idea of needing some common denominators again, and this time the common denominator is going to be 12. Again, take a second, pause the recording, finish this up, see what you get. All right, 2 3/4, that turns into 2 9/12. 2/6 turns into 4/12. This is 2 13/12, which we know to be really 3 1/12. All right, the key here is to not think that we're done yet. This is just one side of the square. So we are actually going to need 4 times as much. The new perimeter we need 4 times 3 1/12. Yeah. Now watch this. This is pretty slick and way faster than you can do on your calculator. When you say this, 4 times 3 1/12, there's an and there, which makes it look like addition, which it is. This is 3 added to 1/12. And you know the distributive property. 4 times 3 is 12. 4 times 1/12 is 4/12. Slick, huh? Which of course is really 12 1/3. These are feet of trim. So the perimeter changes. Okay, you have some homework to do, and I will see you during the next lesson. Have a great day. Take care. Bye-bye.